Hello everyone, this is my part 1 in my real analysis lecture series. I'll be going over these next few videos. I'm going to be helping you guys learn the basics of real analysis, what it is, how to go about proving things, and help get you a basic understanding of this very fundamental topic when you're just starting out as a mathematician. So the purpose of a real analysis class is kind of to teach you the basis of numbers and their properties, as well as how to go about proving things. And it was really built off of a way of defining numbers in a definitive sense, and it really helped people deal with infinity. So I guess to start off, we can talk about what the main types of numbers are. So you might have seen this before, but we start off with the naturals, right? And then based off of that are the whole numbers. And on top of that, we would have integers, which as you might commonly know as the negatives plus 0 plus the regular whole numbers. And then on top of that we would have the rationals, okay, and those are the fractions and 1/2 and those kind of numbers. And then in a broader sense we have all of the real numbers, and then in a subclass we have your irrationals. So that would be like pi or the square root of 2 or something like that. Okay, and what analysis does, it's a way of defining all these types of numbers and their applications, and it gave mathematicians, especially right when they were starting off to define infinities and stuff like that, a way of working with numbers like pi, which as you might know, is non-constructible. You cannot definitively draw a line that is equal to the measure pi, although you can do that with a number like 1/2. So analysis and its methods gave a way for mathematicians to kind of work with infinities and do all sorts of stuff like that. So before we get into the basis of analysis and go into how to construct these numbers. So for today's video, I'm going to talk about what actually is a natural number, whole number, integer, and give you a sense for how real analysts define things. It's very definitive. So, but first, before we do that, we have to go over some basic notation. Okay, so one of the most important notations in analysis is a set. And a set is just a collection of objects. It's usually denoted with these curly brackets, and you can pretty much put whatever you want. It's just a collection of things. You can have squares, you can have numbers, you can have smiley face, whatever you want. It's just a collection of stuff. You can even have a set contained in a set. So a set S, for example, would be part of a bigger set, and that's still considered an object. So, and then after sets, important notation would be this little funky E looking thing, which means element. So if I say, for example, the variable x is an element of the set S, that means I'm saying that then whatever this thing x is in the set S, okay? And then vice versa, if I have a cross through it, that means x is not in the set S. So this would look something like this, sorry, and if this was the set S, okay. Another notation would be this, the 0 with a cross through it. This is considered the empty set, which just means a set with nothing in it, an empty set. Some more notation. A, C, this curve B, this means contains. So, or A is a subset of B, meaning that everything in A is also in B. Or, as I like to think of it, it's a set within a set. So, the set A, which might contain x, 2, and 5, this is A. If I say that A is contained in B, that means that the set B is equal to everything that it might contain. So let's say a smiley face, a square, and then everything in set A. Okay, so there's that. Some other useful notation is a union. And you guys might be familiar with this if you've ever had any previous mathematics education. You might have seen this in other classes. Intersections, complement, and I'll go over this after I write all of it down, minus, and product. So in terms of set notation, all of these things might mean something slightly than you're used to. So a union is, say I have a set A, and I say union, this symbol is for union. B, this means that, so X, such that X exists in A, or X exists in B. So it's everything in set A or everything in set B. Okay, so an intersection would look like this upside down U, B, and it's equal to a set such that X, which is the element we're talking about, any arbitrary element, X exists in A and X exists in B. Okay? So that's saying the intersections between these two sets. So what points are in both A and what set points are in B as well. So then we have the complement, which is A, and it's this little c up there, and that means you want any x that does not exist in A. So let's say the set A. So if the set A was, for example, everything of the color red, then the complement of A would be everything that is not the color of red would be in that set. Okay, so it's just everything that it's not. Then minus would be A take away B. And you're essentially subtracting the two sets. So it'd be X such that X exists in A and X does not exist in B. Okay, so it's A take away B. If you had, say, the set, if I had the set 1, 2, 3, 4, 5 as my set A, and I wanted to have B equal 1, 2, if I did A minus B, then I would be essentially subtracting the 1 and 2, and I'd be left with this as my subtracted set. And product means something slightly different when we're talking about sets than with regular numbers. So if I said A product B, that would be the same thing as saying there is an ordered pair A comma B such that A exists in A and B exists in B. So what that means is that there is a point A or an element A that's in A and there's an element B that's in B. And it's contained in an ordered pair that is somehow related to each other. So they're somehow related to this set, and I'll go into relationships a little further, a little bit later. So, okay, let's go talk about relations. So we have A comma B, right? That's an ordered pair of 2 points, and we want to say that they're related somehow. So a relation is basically some kind of conditioning, some condition of a product of sets. Okay? So for example, if we're talking, in this case it's a binary relation because we're dealing with 2 different sets, a set A and a set B. So if a binary relation R, okay, a binary R is a subset of the relation of the product A cross B, then the ordered pair A comma B in A cross B are contained in this relation. Or sorry, conditioned by this relation. And that's often written as A, R, B. Okay? So, an example of this is the very common equivalence relation. Okay? So this is a relationship that somehow conditions my product sets and forms an ordered pair. And you'll start to see what that kind of vague sentence means with this. So an equivalence relation, let's say R, is a relation on set S such that, and I'll just put SC such that S cross S is 1 A R A. So that's saying that if the element A is applied this relation, it's the same as itself. It's what we call reflexive. 2 would be ARA, then ARB, then BRA. Okay, so if the relation if A is related to B, then B is related to A. So that's another condition. So what I'm doing is essentially giving the axioms or conditions for my relationship. 3. So if A are B and B are C, then A are C. And these are respectively known as the reflexive, the symmetry, and transitive properties. And you might be more familiar with this R if I had say put an equal sign, because that's essentially what this equal sign is. It's a relationship that is applied on such a set which contains ordered pairs A comma B, right? And this equal sign conditions these ordered pairs in such a way that A can equal A. If A equals B, then B equals A. And if A equals B, B equals C, then A equals C. So that's kind of what a relation is. And that's going to be very important going forward. So to start off, we want to talk about the natural numbers. Right? This was kind of the basis of our number graph that I showed earlier, and it's the basic thing that you can have, essentially. The basic definition of what a number is and what counting is. So it's based off of 5 particular axioms. And an axiom is just a fancy way of saying a special definition. Like absolute definition, kind of just take it for what it is. So the axioms for the natural numbers, once I lay them out, we'll be able to construct a set that contains all of the natural numbers that you're familiar with, 1, 2, 3, and so on, all the way up to infinity. So let's say we have set T, for which 1, T is non-empty and has an element we'll call it 1, okay? Number 2, there is a function, and a function is another type of relation, right? It's just a way of conditioning ordered pairs and giving them some kind of a condition, right? So the function S, we'll call it the successor function. Okay. With domain T and range contained in T, i.e. for every A in T, so if we have an element A in T, then S of A is also in T. And S of A would be, of course, the successor function. And once that function is applied to an element, you're not going to go out of the set T. So we're basically just arbitrarily saying everything is contained always. Okay. 3, for any A and B in T, if SA equals SB, then A equals B. Okay? And that's saying that the successor function, if 2 successor functions on an element that are supposed to be different, or we assume that they're different, that cannot be the case. If 2 successor functions are applied to 2 elements equal each other, then those 2 elements must be the same number. Okay, and that's what A equals B. 4, for any A in T, S of A is not equal to 1. Okay, so basically, if you apply the successor function to any element, you're never going to get your original element, the starting element, 1 again. And then 5, if K is any subset of T which contains 1 and for which if A is in K, then automatically S of A is in K. k, then k is equal to t. Okay, so that's saying if you create a subset of t, so basically section off a part of t, which contains its original element 1, and for which, if it isn't in k, then automatically the successor function of, if any a isn't in k, then automatically its successor is also in k. And that forces k to equal t. And we'll go into this further. Based on these 5 axioms, we can create a set that approximately looks like this. It allows us to construct a set where we have a starting point, and then it brings us to a next point, and it brings us to the next point, and it brings us to the next point. So essentially what we've done is we've constructed a set. As long as we've constructed a set that follows these 5 axioms, we will call this set the natural numbers. Now notice we haven't talked about the numbers 1, 2, 3, 4. We just have a notion of counting, and that from one point we can go to the next point, and to the next point, and to the next point. According to the rules of set theory, there is such a thing as an empty set, which we've denoted as a 0 with a cross through it. And given any collection of sets, there is such a thing as a set containing of the members of the collection, and that new set is different from its members. So, in particular, for example, if we had a set consisting of 0, 0, and it's denoted this is different than this, and the set containing those sets denoted across, comma, right, is different from each of those, and so on. So the first element of the collection, so constructed, is denoted as 1, okay, and the subsequent constructions are the corresponding successors. So if we start off with 1, maybe we go to 1, 1, then we go to 1, 1, 1, then we go to 1, 1, 1, 1, 1. Ignore that last part. If we want to consider what our natural numbers will kind of look like before we've constructed the concept of addition and multiplication, this is probably the most convenient way of talking about our numbers and their successions. Okay, so of course, n usually refers not to just the set, but the set within 2 main operations defined on it. And those 2 binary operations will be commonly known as plus and multiply, right? So these operations representing addition and multiplication, and let's define them. So our natural numbers are consisted of these 5 axioms, which are essentially saying that we're starting at a number 1, and then we're continuously successing to further numbers, as well as a notion of, so we have axioms, and we have operations. So if we want to define these definitively, for addition we can say for any a in n, we set a plus 1 equal to SA, that is the successor of A, the number that comes right after A, then for any B in N, right, for which A plus B is defined, we set A plus S, successor of B, and we say that that would be equal to the same thing as the successor of A plus B. And if you want to take it a step further, this basically is saying that A plus B plus 1 is equal to A plus B plus 1, essentially. Right? So that gives us a notion of addition, okay, which we can work off of. Now for multiplication, if we want a notion for that, we can define it as for any A in N, we set A cross 1 is equal to A, meaning that 1 is our identity. And then for any B for which A cross B is defined, we can set A cross the successor of B equal to A plus A cross B. And this gives us a notion for what multiplication means within the natural numbers. So these 5 axioms and these 2 binary operations give us the basis for working with the real numbers and numbers in general. We define the order relation also in the natural numbers in a similar fashion. So if we want to talk about order, we're simply talking about this little less than sign, and if we want to define it, A less than B means B follows A in the successor relation. Meaning that if B is greater than A, that means it's somewhere farther down the line in that successor chain, that arrow, those arrows and points. So if we want to go from natural numbers to integers, which are usually denoted by this funky Z, okay, it's pretty straightforward, and even other related constructions, it's often the case that we deal with the positive numbers first and then mirror the construction to get the negatives. So before we go to the integers, we have to first go to the whole numbers, which often is taken for granted. So the whole numbers colloquially is known as the natural numbers plus 0, but we cannot talk about 0 without first giving it a definite definition. So first we take an object. Let's just call this object 0, or give it this shape of a squished donut. It's not an n, but we define it as this. 0 plus a is equal to a plus 0, okay? Which is the operations that we talked about before. And then, this isn't a minus sign, by the way, just underlining. Then we say 0 cross a is also equal to a cross 0, okay? And then we set 0 is in fact less than our original first element in the natural numbers 1, which we gave the symbol of a downward line, okay? So again, addition and multiplication are defined on W, the whole numbers. We can see them to be commutative and associative and distributivity we can see that the commutative and associative properties and distribution properties hold, and that now in addition to 1 being the multiplicative identity, 0 is the additive identity. Then we can use addition and multiplication to give us ways of representing the elements of W using a finite collection of symbols and a place value notation in the base 10. So at the end of the day, all we're doing when we talk about numbers is we're giving symbols definitions based on basic axioms. So these are the foundational axioms that we can base our language of mathematics on. Then we can further go on by giving specific symbols, for example, addition, multiplication, ordering, or even the number 0. These definitions, we can go on by saying that if we work in the base 10, then instead of using points and arrows and points and arrows, we can instead use these symbols, which we commonly known as our basic number system. So, and this goes on, we have until 9, and then if we want to talk about the whole numbers, we include a 0, and we go from there. So we're about halfway through. We've got the natural numbers, we have the whole numbers. Now what we need to do is construct the integers, and then go forth and construct the rational numbers. And we'll continue to construct the reals at another time, but not in this video. That takes much more rigorous proof. So to construct Z, we will look at the union of the whole numbers and a distinct copy of the natural numbers. In this distinct copy, we'll be using symbols of -n rather than the corresponding n's in our original natural number set, okay? Which we know as 1, which is equal to 1, 2, 3, and yada yada, right? Infinite. Okay, so we have this new symboling, so we need to define it, right? So we're going to define it first as using these two bars, which we'll call absolute values. We're going to say that with these two bars, the absolute value of the -n is the same thing as the absolute value of the regular n. And we define absolute value as something that just removes this, for our purposes right now, just removes this minus symbol. We then let Z be this union with this notation. So we take our basics 1, 2, 3, 4, so on and so forth, and then we're going to have the union of this with our element 0, which this would be equal to the whole numbers, and then the integers would just be this 1, 2, 3, dot, 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 which is our n, union our 0, and then just take our -n, right, union. So what we've done here, not only are we expanding our uses of our original numbers, right? But we're also extending our use of addition and multiplication to all of Z by considering the corresponding new cases. Ignoring 0, of course, the 4 cases are the sums or products of 2 positives, positive and negative, negative and positive, and 2 negatives. And it is very tedious but straightforward to verify all 6 of the arithmetic axioms, commutativity, associativity, and the identity elements for both operations and distribution still hold. In addition, every element has an additive inverse. So while this can be very tedious and it is generally straightforward, but the general idea is that we're keeping this natural number and we're expanding the definition simply by adding a new symbol, the minus sign, and we're saying that the minus n is the absolute value of the minus n is equal to the absolute value of the original n. Okay? So with that, we have a basic understanding of integers. So now the passage to rational numbers. So that is Q, rational, right? And this is also direct, but illustrates another element that appears in analysis, the need for care and making sure that things are well defined when a definition is made that depends on the particular representation of objects that have more than one representation. Okay, so what we're saying is we haven't, what I'm basically trying to get to is that when we're talking about rationals, we have a problem where we have 1/2 is equal to 2/4 is equal to 3/6, right? And this provides an interesting dilemma in definitions, a straightforward one, but one that says we need to be very careful about how we define things. Okay. So to begin, we define Q by first consider the set F of all ordered pair integers whose second entry is 0. So we're talking about a product of z and z, so our two integers, where we have a, b, where b cannot equal 0. Okay, and that's basically saying that you cannot, remember when we're talking about rationals, you cannot divide by 0, it's just undefined. From this, we can define an equivalence relation, where we have an A over B somehow equal to C over D. And to get specific, this would be the same thing as saying, so A times D has to equal B times C for these two to be equivalent. And this is going to help us with this dilemma presented here. So what we're going to do is we're going to say this is our equivalence, I spelled that wrong, relation for our rationals, okay? And you'll see that when defining the summer product of two elements of Q, that is defining a function on Q. No. And, okay. And this sounds somewhat vague, but realize that, for instance, defining a number a of an element of Q is not the same as defining a function on Q, because 1/2 and 2/4 are the same, but their numerators are different. While defining the summer product of two elements of Q is defining a function on Q, as we shall see further. For AB and CD in Q, we'll set that A over B plus C over D is equal to ACD plus BC over BD. And note that the symbols on the left-hand side from each equation are the new operations, while those on the right-hand side are the ones known in Z. Now from their definition, this is not the case that, example, 1 over 2 plus 2 over 3 and 2 over 4 plus 2 over 3 are the same. They have different representations until you start replacing things with their equivalent expressions, and that goes the same for the multiplication of the two. So this times this, and this times this. So while intuitively we know that these are the same, if we're talking about it in a literal sense, not the same. Okay, so we get very, very deep into the details with analysis, and you cannot simply say they're the same until you fully bring this into its equivalent relation. Okay, so to demonstrate that these operations are well defined, you need to check them for generic choices of the two inputs, which means a total of 8 generic integers, 2 for each numerator and 2 for each of the two denominators. Tedious but straightforward, and I would recommend you try and check and try to see for yourself if you can verify this. All you use in the verifications are the known properties of the integers and the definitions of equivalence in Q, which we have here. So this is our definition of what equivalence means with two rationals. So with that, if you don't already see it, we kind of have created the rational numbers, because simply with numbers in the form m over n existing in the set Z, where n cannot equal 0, this right here, where just getting into the tediousness of how to write a set. So if this is Q, that's equal to this m and n, where m and n exist in the integers, and they are not, and n cannot equal 0 because you cannot divide by 0. This is every single rational number you could ever think of. So if you wanted to list them, for example, you would start by one. You would start with 1, right? Because you can't. You could start with 0 really, and then you start with 0. You have 1. Those are your two basis, whole numbers and natural numbers. Then you go to 1 over 2. Okay. Then you go to 1 over 3. 2 over 3, 1 over 4, not 2 over 4 because that would be equivalent to 1 and 2, 1 over 2, and then you have 3 over 4, and if you kind of see this pattern, through this you can construct every single rational number in existence, and this is an infinite series that does obviously not converge. So we have our key set satisfying the full condition of 9 axioms that define a field. When we use the term binary operate. Okay, so we have the basis. We have our naturals, which we define as points to points. And then we further define this as 1 to 2 to 3 with a successor function, which we might also know as a plus 1. And then with this, we've also added a notion of what is addition and multiplication. And then on top of that, we have our whole numbers with our definition of the number 0. And then from the inverse of the naturals and adding the wholes, we can construct the integers. And then further from that, we can use the integers to construct our notion of rationals. Rationals, so m over n, generic, okay. Let's now go into the definition of a field, okay? A field is just a set with at least 2 distinct elements, which will denote 0, 1. They have to at least contain 2 distinct elements. For right now, we're gonna, for example, 0 and 1, okay? And 2 binary operations, which we used plus and minus, for all of x, y, and z in the field. On top of that, we want all of our binary operations to be closed, okay? So that means that the operation is, so a closed operation is operation defined on the product of the set with itself and produces an element within the set. Okay? So what we're saying is that anytime we apply the operation to the set, we create an element that is still inside the set. So we're not leaving our bounds of our set. So if we have the number 1, we apply our operation, and if we get the number 5, for example, we're still in our bound of natural numbers. Okay? So that's what we mean when we say closed. It has to at least have 2 of those. And that would be what a field is. For furthermore, a field must contain the following properties. Contain the following axioms. A1, x plus y is equal to y plus x. So that's commutative property. And then A2 would be x plus y plus z is equal to x plus y plus z. So that's associative. And I'm going through the basic axioms that are based off of our two operations, remember, and based on our basic understanding of what elements are and their successors. A3, which is 0 plus x is equal to x plus 0 is equal to x. So this is the additive identity, right? A4, that there exists an element which we can denote as negative x such that x plus negative x is equal to negative x plus x equal to 0. And this is, of course, with our understanding of integers. If we have 1 and its converse, negative 1, then that's just going to equal 0. M1, so that's x. Don't want to get confused between the x and the multiply sign, so I'll do that. Times y is equal to y times x. And this is the commutativity property of multiplication. Then furthermore, M2, we're going to have a similar associativity with x times y times z is equal to x times y times z. Okay, and then we're going to have our identity, of course, which is number 1. It's equal to 1 times x. So that's our identity for multiplication. And 4, squeeze this in here. So we have an element which will donate, so we haven't really gone into this, but to the negative 1 that satisfies, so we have some, so there exists an element, x to the negative 1, that creates an equation such that x times this element is equal to the, of course, this is the commutativity of this element, and this is equal to the identity. So the existence of multiplicative inverses. And then finally, we have D for distributive, where x times y plus z is equal to x times y plus x times z. Okay? So that's the distributive property of multiplication over addition. And again, the verification of these 9 properties on Q is tedious but straightforward and uses only the definitions and the already established properties in Z. And these create a field which contains our rationals, our integers, our whole numbers, and our natural numbers. And of course there are other sets we already know which satisfy all these properties. The integers modulo a prime number are a nice finite example, and the field of quotients of real polynomials of a real variable is another. We will examine a few things in the future that are automatically true for all fields before going on to the properties that make Q more special. Okay, So thank you for watching this tutorial, this lecture kind of on real analysis. I'd really appreciate it if you hit that subscribe button. Leave a comment if you have a suggestion, or if you want to add some topics or have me talk about something for a future video. I'd love to hear you guys, what you guys think of this. If you have any tips for me, I'm pretty new at this as well. So yeah, go and do that. Hit the like button, all that good stuff. Thank you.